Hi, welcome back. We're still in Unit C, which is our physics unit on electromagnetic energy. And in Chapter 1, this is the final lesson of Chapter 1, and this is all about transmitting electrical energy. In this lesson, we're going to be looking at power now and energy, electrical energy, and we've got two new equations for those concepts. And then we're also going to be looking at transformers, and we have a equation also for transformers that we're going to be dealing with. And we're going to be looking at AC and DC current again and some of the advantages for transmitting and using this electrical energy. So we have our textbook pages that these concepts are part of. If you want to focus your attention on the textbooks, it also covers all the concepts that we're looking at. Right, so power can be defined as the rate of doing work or transforming energy. The units for power are watts or joules per second. So 1 watt is equal to 1 joule per second. And the equation, so we've got two equations for finding power. So there's two. So there's our power. P is representing power. And remember, the units are watts. So power can equal current times voltage. So there's our one formula, our first one. Or power can equal current squared times resistance. So there's our second formula. Now, you're familiar with current and resistance now and voltage from Ohm's law. So you may need to use Ohm's law to find one of these missing variables sometimes. All right, so depending on what information is given to us, it'll determine which of these two power formulas we're going to use. So these power formulas can be rearranged. So here's our first power formula, P equals current times voltage. You can use this triangle if you want, or here are the rearrangements of that formula to find what's missing. Our second formula, P equals current squared times R, or resistance, is over here, also in a triangle if you want to use it, but here are the rearranged formulas. Remember that since I is squared, or current is squared in this power formula, if you're going to try and find I, you're going to have to take the square root of the power over R squared. But for the majority of the questions you're going to be doing, you're going to be looking for power. You're going to be finding power. So let's try a practice problem. Calculate the current running through a 100-watt light bulb with a resistance of 15 ohms. All right, so let's write down what we know. So we know we have 100 watts. Well, watts, that's a measure of power. So let's write that down. So we know the power. All right. I just said we weren't going to have to do these kind of questions, and we're going to. That's so funny. Resistance. We know the resistance is 15 ohms. And we want to find the current. Current, remember, it's not C, it uses I, variable. So we're looking for the variable I, or current, and we have resistance and we have power. So this is what we're looking for. And we have resistance and we have power. So we have to use this equation here because we have two of the variables and only one is missing. So that's the equation we want to use. So we're going to have to rearrange for I, and our rearranged formula, we can go back here if we want to see. This is our rearranged formula here. So I is equal to the square root of P divided by R. All right, so I is equal to the square root of P divided by R. All right, so let's sub in our values. So the power is 100 watts. Our resistance is 15 ohms. So we're going to do 100 divided by 15. All right, so that 100 divided by 15 is 6.666. I'll just round it to 7 at this point, but it's a lot of 6's. And then lastly, we take the square root of that number, so the answer is 2.58197. And we're going to look back to see how many significant digits we have. Resistance only has 2, so that's our limit. So are going to change this to 2.6, and we just found current I, so our units are amps. So 2.6 amps is our final answer, and we can just verify that with our answer here. All right, so let's try another question. So it's all, figuring out which formula we need is all in identifying the variables that we have and what we're looking for. So let's take a little longer to look at that. A speaker has a resistance of 4.0 ohms and allows 2.0 currents of current, 2.0 amps of current to flow through. Calculate the power consumed by the speaker. All right, so we have resistance is 4.0 ohms. We have a current I of 2.00 amps. And we have power consumed by the speaker. We don't have power, sorry. That is what we're trying to find. Excellent. Okay, so we are looking for power, but we have resistance and current. So we have resistance, we have current. So again, we're going to be using the same formula here, but in this case, we don't have to rearrange the formula because we're trying to find P. So we'll just write the formula as is. So power is equal to I squared, so current squared, so 2.00 amps squared times our resistance of 4.0 ohms. So 2 squared is just 4. And then we're going to multiply by 4. Yeah, we shouldn't even need our calculator here. So 4 times 4 is 16. We'll look at our significant digits. Our ohms was only 4.0, so we can only have 2 significant digits in our answer. And our answer is power, and our power is measured in watts or joules per second, so we'll do watts. So our final answer is 16 watts. All right, so using power and energy consumed, utility costs can be calculated. So first we need to figure out how do we calculate the energy, and then we can actually figure out how much our energy is going to cost us. So again, this equation is on page 3 of the data booklet, along with the other ones we just did. But now we're going to be finding energy. All right. And remember, okay, so energy, if you think back to Science 10, you might remember that your energy is measured in joules. And remember, we just learned that power is measured in watts, and 1 watt is a joule per second. So if we multiply our power, which is joules per second, times our time in seconds, our seconds will cancel out and leave us with joules, and that's where the energy, joules, comes from. So energy can be expressed in joules, but it can also be expressed in kilowatt hours. And you're going to see that if you look on any of these energy guides for like your dryer or freezer or something like that. Any big appliance will have one of these, and that's going to tell you how much energy is consumed per year approximately by that appliance. So we can use that to calculate our cost to run an appliance. But depending on what our question is asking for, we need to convert our variables so that we end up with the right, the energy in the right units, either joules or kilowatt hours. So if you want your energy in kilowatt hours, then when you're finding energy in your formula, power times time, you want your power to be in kilowatts and your time to be in hours. So you make those unit conversions happen before you put them into the equation. If you want your energy in joules, then you're going to make sure your power is in watts and your time is in seconds when you put them into the equation. Right, so let's take an example here, look at an example. If a 40-watt bulb is on for 2 hours, how much energy does it use? So if we're trying to find energy, let's see what we have here. We've got a 40-watt bulb, so we know our power is equal to 40 watts. We know our time is 2 hours. And now we want to know how much energy, but we want to know the energy in joules, right? So if energy is in joules, then we need our power in watts and our time in seconds. So remember, I'm just going to go back here. If we want our energy in joules, we need our power in watts and our time in seconds. All right, so we need to do a conversion. Yeah, so we've got our energy, our power is in watts already, but our time is in hours. So we need to turn that to seconds. So to turn to seconds, we're in hours right now, so we're going to have to multiply by 60 minutes per hour, and then multiply again 60 seconds per minute. So we're going to end up multiplying by 3,600 when you see that. Okay, so that's what this is telling you down here, 60 times 60. All right, so let's plug everything into our energy equation. Just gonna undo that. So energy is equal to power times time, and our power is 40 watts. And our time is going to be 2 times 60 times 60, which is 7,200 seconds. So we multiply 40 times 7,200 and we get 288,000. And these are watt seconds or joules. Now we have to watch. We can only have one significant digit in our answer. So we're going to have to put this into scientific notation. I'm going to round that 2 up to a 3. I have to put my no decimal 0. So 3 times 10 to the 1, 2, 3, 4, 5 joules. So our final answer is 3 times 10 to the 5 joules. So this should actually just be a 3, not a 2.9. All right, let's try another problem where we're looking at kilowatt hours this time. So did you know that most models of TVs and DVD players use electrical energy even when they're turned off? This standby power is used to run clocks and to provide instant on feature, allowing electronics to become operational with a click of the remote control. Average values for standby power are about 8.0 watts. Since this power is required 24 hours a day, the electrical energy consumed is significant. Determine the electrical energy required to supply 8 watts of standby power. So, 8 watts of standby power for both a TV and DVD player during 1 year. Express your answer in kilowatt hours. All right, so first thing we want to do is write down the variables. We have our power of 8 watts, and we know our time that we're looking for is over a whole year. What we're looking to find is the electrical energy. So energy is what we're looking for. And in this case, it tells us we want the energy in kilowatt hours. So those are our desired units. So if we want our energy in kilowatt hours, remember our power is going to have to be into kilowatts and our time is going to have to be in hours. Because when we multiply them together, we get kilowatt hours. So first thing we're going to need to do is change our power of 8 watts to kilowatts. And kilo is just like kilometers. Kilo is 1,000. So we're going to divide our 8 by 1,000 and we'll get our kilowatts. So 0.008 kilowatts is our power. Then we have our time in years, and we're going to need to change years to hours. So in 1 year, there are 365 days in 1 year times how many hours? Oh yeah, this is days, 365 days, and there are 24 hours in 1 day. So when we multiply this all out, our days will cancel out, our years will cancel out, and we'll be left with hours. So 1 times 365 times 24, which gives us, I'll just put it down here, 12,410 hours. And I won't get our significant digits right now. We'll deal with that at the very end. So let's put in our formula. Energy is equal to power times time. Our power we just found, and remember we had to convert it so it was in kilowatts. So 0.008 kilowatts times our time, which we just found in hours. So 12,410 hours. And we multiply these together, which gives us 99.28. Oh, made some kind of little error there. So when 0.008 is multiplied by 12,410, you actually get 70.18. And let's just take a look at our significant digits. We only had, well, technically we only had 1 year there. But our answer does have 2 digits. Oh, no, that's only 1 significant digit. If we change it to 70, then that 0 doesn't count as significant. So 70, and then our units are kilowatt hours. Okay, so that's our final answer, 70 kilowatt hours, because we had kilowatts multiplied by hours, so we got to the right units. Okay, so now we're going to take this a step further. In part B, you'll see they start adding price in. So if the price of electricity is 9.3 cents per kilowatt hour, determine the cost in dollars of providing standalone power to the DVD and TV for 365 days in 1 year. So if we're finding cost, it's going to be equal to the power times the cost per power unit, whatever the power unit is. Because we found our power in kilowatt hours, our cost is also given to us in kilowatt hours. It's cents though, so keep that in mind. So it's 9.3 cents. So when you multiply the power that we use, the 70.08 kilowatt hours, times the 9.3 cents, our answer is also in cents. So to change that to dollars, remember you have to move the decimal over by 2, because 651 pennies or cents is $6.52. So there's about 2 million TVs and DVDs that operate with standalone power in Alberta. And use that fact to estimate the total annual cost of maintaining standby power for all these devices in Alberta. So if it costs for one 6.52, then let's multiply it by the 2 million TVs and DVD players. And you're going to see that's quite the cost for everybody in Alberta to have their TV and DVDs in standby power. $13 million. All right, so this last example actually has quite a few little pieces to it. So it can be a little bit trickier, but let's see if we can identify what we need to do. So first off, a light bulb operates on a 100-volt circuit and draws 0.91 amps. Assume you turn on the lights for 12 hours a day. What will it cost per day if utility rates are 7 cents per kilowatt hours? So let's write down what we know. We know we have our voltage of 100 volts. We know our current, I, is equal to 0.91 amps. And then we know some other things. We have time, which is 12 hours. And we have a utility rate of 0.07 per kilowatt hours. All right, and we're trying to find the cost per day. or the cost for this time. We already have the per day here, so we're just trying to find cost. Now, to find cost, we need to be able to multiply this rate here by the power in kilowatt hours. So what we're looking for is power in kilowatt hours. So that's power in kilowatts. And then we can use our power to find our energy in kilowatt hours, which we can multiply by our rate. So first step we're going to do is find our power. So power is equal to current times voltage. Once we have our power, then we can use the equation energy equals power times time. And that'll give us our energy. And then once we're all done and we have our energy, then we can figure out our cost. And that'll be equal to the energy times the rate. All right, so let's start with our power, current times voltage. So we're going to put our current of 0.91 amps in and our voltage of 100 volts. So this will give us a 91. And our units for power are watts. Alrighty, but remember we want our units for power to be in kilowatts. So we're going to have to divide by 1,000 or move our decimal over by 3 to get to kilowatts. So 0.091 kilowatts. All right, once we have our power in kilowatts, we can put that into our energy equation. So power is 0.091 kilowatts times our time, which is 12 hours. And we want our time in hours, so when we multiply our kilowatts by hours, we get kilowatt hours. And that gives us 1.092 kilowatt hours. All right, so now we know our energy. We can plug that into our formula down here, 1.092 kilowatt hours. And we're going to multiply it by our rate, which is 7 cents, 7.07 per kilowatt hour. So we multiply these together, we get 0.07644. And we're talking about cents right now. And that's basically, we have to round that up to just one decimal or one significant digit. So we're dealing with 8 cents is what we're dealing with. So that costs 8 cents. And that is where I'm going to stop. That's the end of the first half of this lesson. There are a lot of different formulas that you learned here. So you've got 2 different equations to find power. Then you have an energy equation where you can use different units. And then you have the cost equation. So make sure you do your practice questions now and refer back to this video and the slides to help you with those practice questions.